Aeolian processes and landforms. Objectives. After attending this lesson, the user would be able to comprehend the nature of wind as a geological agent and the role played by it in creating various landforms called as Aeolian landforms. This lesson highlights all the features of erosion, transportation, and deposition that are made by wind. Wind is a powerful geological agent. Introduction. Earth is a dynamic evolving system. Many geological processes are active on the surface of the earth. They are called as exogenous processes. The notable surface geological processes are weathering, mass wasting, erosion, transportation, and deposition. These processes are capable of creating both constructional and destructional landforms. If any of these Earth's processes are done by a natural system on the surface of the Earth, then it is called as a geological agent. Notable geological agents. The geological agents are capable of eroding, transporting, and depositing the Earth's surface materials from one place to the other. The prominent agents are running water, glaciers, wind, waves and currents, groundwater. These are also responsible for creating numerous landforms all over the surface. Work of wind. The work of wind is expressed in different climatic zones, but is greatest in dry climatic zones. The dry climatic zones are characterized by sharp diurnal temperature variations, low precipitation 200 to 250 millimeters per year, excess of evaporation over precipitation 5 to 15 times, sparse vegetation or complete lack of vegetation, frequent winds of great force, presence of unconsolidated, very loose, easily erodible surface materials. Such conditions are specific to deserts. The work of wind is more in deserts and dry zones. Desert conditions in the globe. The deserts and semi-deserts occupy about 20% of the surface of continents. Especially great areas are occupied by deserts in Asia, Africa, and Australia, less in Europe, North and South America. The great sand seas that completely cover large areas of North Africa's Sahara Desert, Saudi Arabia, and Central Australia are the most spectacular examples of wind activity on Earth. There are two main deserts in India, the Thar Desert, which is the seventh largest desert in the world, and the Kutch Desert, bordered by the Arabian Sea. Wind as geological agent. Wind has the ability to shape the surface of the earth. Wind is one of the greatest agents of land erosion and transportation. The action of wind is very significant in arid and semi-arid regions. Due to profound wetness, wind cannot act in humid regions. Wind is capable of eroding, transporting, and depositing the surface materials in dry lands. The landforms created by wind action are called as Aeolian landforms. The word Aeolian is derived from the Greek word Aeolus, meaning the god of the winds. Aspects of study. Aeolian landforms are features of the Earth's surface produced by either the erosive or constructive action of the wind. Winds are effective agents in regions with sparse vegetation and a large supply of unconsolidated sediments. The major aspects to be studied in geomorphology and physical geology are Wind and its characteristics, geological processes of wind, erosional landforms, transportational effects, and depositional landforms. Wind and its characteristics. Wind is a moving mass of air. Air, by nature, is a dynamic system. It moves due to pressure differences. The basic driving force of air movement is this difference between two regions. The air pressure is described by several physical laws. The horizontal pressure difference provides the horizontal force or pressure gradient. The greater the pressure gradient, the greater is the force on the air, and the higher is the wind speed. The circulation of air over the Earth's surface makes the wind to blow. This wind has a greater mechanical force to do many things on the land surface. Wind and arid regions. Wind is common in arid desert regions. Air near the surface is heated and it rises. Cooler air comes in to replace the hot rising air, and this movement of air results in the generation of winds. This wind has the ability to transport, erode, and deposit the sediments. Arid regions have little or no soil moisture to hold such sediments, rock, and mineral fragments. Wind has the ability and force. The work of wind comprises the processes of deflation, corrosion or abrasion, saltation, and accumulation or deposition. In nature, all these effects are closely interrelated and essentially constitute a single complex process. Some actions are predominant in certain specific conditions. Prevailing wind patterns are determined by variations of solar radiation with latitude, the Coriolis effect, deflection due to Earth's rotation, the configuration of continents and ocean basins, and the location of mountain ranges. Deflation. The blowing out and scattering of rock particles by wind is called as deflation. This term is originated from the Latin word deflare, means blow away. The surface of any desert is covered by diverse fragments of rocks, sands, soils, and dusts. These are arid zones. In such arid zones, streams and jets of air can blow out the sands and rock particles. First, the blowing wind clears the sandy and fine-grained materials and leaves the coarser fragments behind. These form the rocky deserts. Such rocks are again weathered or fragmented, and then, once again, deflation becomes active. Deflation is the lifting and removal of fine, dry particles of silt, soil, and sand by the blowing wind. Impacts of deflation. Deflation is the lowering of the land surface due to removal of fine-grained particles by the wind. Deflation concentrates the coarser-grained particles at the surface, eventually resulting in a surface composed only of the coarser-grained fragments that cannot be transported by the wind. Such a surface is called desert pavement. Velocity of wind. The effective force of a wind depends on its velocity. Even with little velocity, wind can lift most of the fine dusts. Both stony and rocky deserts are formed due to deflation. Wind speed is affected by a number of factors and situations, operating on varying scales, from micro to macro scales. These include the pressure gradient, Rossby waves, and jet streams, and local weather conditions. There are also links to be found between wind speed and wind direction. The velocity of wind is determined by the movement of air from an area of high pressure to an area of low pressure. The velocity will be highest when there is a great difference between the high pressure and the lower pressure region. How close the two pressure regions are will also affect the speed of the wind. How to measure wind? The two most important things about the wind are its speed and direction in which it is blowing. We use a weather vane or a wind sock to see wind direction. It is expressed in compass points. Wind speed is measured by the Beaufort scale, wind socks, or by special scientific instruments called anemometers. The unit of measurement is kilometers per hour, kmh, or knots. The knot is a unit of speed equal to 1 nautical mile, that is 1.852 kilometers per hour. Worldwide, the knot is used in meteorology and in maritime and air navigation related activities. A length of 1,852 meters is the length of the internationally agreed nautical mile. The Beaufort scale. The Beaufort scale is an empirical measure that relates wind speed to observed conditions at sea or on land. Its full name is the Beaufort Wind Force Scale, although it is a measure of wind speed and not of force in the scientific sense. The Beaufort scale was invented in 1805 by Admiral Beaufort to estimate wind speed through observations of objects. The original scale was for use at sea, but it has been adapted for use on land. Abrasion. Abrasion is the mechanical scraping of a rock surface by friction between rocks and moving particles. It happens during their transport influenced by wind. It involves the process of corrosion. The particles transported by wind can strike the obstructing materials along its path. This forceful action of wind with such particles on rocks is called corrosion. Corrosion can do grooving, scarring, polishing, and grinding of rocks. The intensity of corrosion depends on the size and density of carrying materials and also the Earth's surface rocks. If the rocks are very soft, their removal is rapid. Saltation. Saltation is the intermittent, leaping movement of particles of sand or gravel as from the force of wind. It is an action of movement and transportation. It also includes rolling of materials along the surface. In geology, saltation, from Latin saltus, deep, is a specific type of particle transport by wind or water. It occurs when loose material is removed from a bed and carried by the fluid before being transported back to the surface. Deposition. Deposition is the geological process by which the materials carried away by wind are settled when the velocity gets declined. It also happens when there are obstructions. All these create new and new Aeolian landforms. Forces of wind. The forces of wind that are responsible for all these mechanisms are of two kinds, as driving and resisting forces. Winds adopt three mechanisms for eroding the mass: lift, bombardment, drag. Lift. The lift results from combination of wind velocity and turbulence. There is a threshold or critical velocity which is a function of particle size and cohesion, and turbulence, which changes in wind speed and direction. As turbulence increases, susceptibility of particles to lift increases. Bombardment. Bombardment is the collision of moving particles with stationary ones or with solid surfaces. It has abrasion. In this process, there is also collision with the solid surfaces. Drag results from difference in force exerted on windward versus leeward side of particles, or difference in force exerted on top versus bottom of particles. Drag also initiates sliding and rolling. It doesn't lift particles off the ground. Power of wind. The power of wind to erode surface particles is controlled primarily by two factors: wind velocity and surface roughness. Erosive force increases exponentially with increases in wind velocity. For example, a velocity increase from 2 to 4 meters per second causes an 8-fold increase in erosive capacity, while an increase in wind speed from 2 to 10 meters per second generates a 125-fold increase in its erosional force. Consequently, fast winds are capable of causing much more erosion than slow winds. At ground level, the roughness of the surface plays an important role in controlling the nature of wind erosion. Boulders, trees, buildings, shrubs, and even small plants like grass and herbs can increase the frictional roughness of the surface and reduce wind velocity. Vegetation can also reduce the erosional effects of wind by binding the soil particles to the roots of plants. Wind deflation zones. Regions which experience intense and sustained erosion are called as wind deflation zones. The major deserts of the world, the Sahara, the Arabian, the Kalahari, and the deserts of Australia, are near 30 degrees north or south of the equator. Desert pavement. Most Aeolian deflation zones are composed of desert pavements. Almost half of Earth's desert surfaces are stony deflation zones. The rock mantle existing in desert pavements protects the underlying material from deflation. Desert varnish. A dark, shiny stain called desert varnish or rock varnish is often found on the surfaces of some desert rocks that have been exposed at the surface for a long period of time. Manganese, iron oxides, hydroxides, and clay minerals form most desert varnishes and provide the shine. Blowouts. Deflation basins called blowouts are hollows formed by the removal of particles by wind. Blowouts are generally small, but they may be up to several kilometers in diameter. Wind-driven grains abrade landforms. Grinding by particles carried in the wind creates grooves or small depressions. Blowouts are sandy depressions in a sand dune ecosystem, samosir, caused by the removal of sediments by wind. Blowouts occur in partially vegetated dune fields or sand hills. A blowout forms when a patch of protective vegetation is lost, allowing strong winds to blow out sand and form a depression. Although they generally remain small, blowouts can expand to kilometers in size and up to around 70 meters in depth. Ventifacts. Ventifacts are rocks which have been cut and sometimes polished by the abrasive action of wind. Ventifacts are rocks that have been abraded, pitted, etched, grooved, or polished by wind-driven sand or ice crystals. These geomorphic features are most typically found in arid environments where there is little vegetation. Yardangs. A yardang is a streamlined hill carved from bedrock or any consolidated or semi-consolidated material by the dual action of wind abrasion, dust and sand, and deflation. Yardangs are up to tens of meters high and kilometers long and are forms that have been streamlined by desert winds. Yardangs become elongated features typically 3 or more times longer than wide, and when viewed from above resemble the hull of a boat. Sediment types. In Aeolian processes, wind transports and deposits particles of sediment. The particles deposited are of sand, silt, and clay size. The particles are entrained in by one of four processes. Creep occurs when a particle rolls or slides across the surface. Lift occurs when a particle rises off the surface due to the Bernoulli effect. If the airflow is turbulent, larger particles are transported by a process known as saltation. Effects of wind erosion. The first effect is the winnowing of light particles. Wind erosion is very selective, carrying the finest particles, particularly organic matter, clay, and loam, many kilometers. The buildup of this alluvial matter, stripped by the wind from the periglacial steppes, gave rise to the fertile Loess soils that cover large areas of Europe and North America, where highly productive farming has developed. The most spectacular forms are dunes formed by winds. These are mounds of more or less sterile sand, which move as the wind takes them, even burying oases and ancient cities. Factors affecting the extent of wind erosion. The factors affecting the extent of wind erosion are aridity of climate, soil texture, soil structure, state of the soil surface, vegetation, soil moisture. Desert environments. Desert environments are characterized by very low mean annual rainfall of less than 250 millimeters, absence of vegetation, very high daily and annual range of temperature, dust storms, high velocity winds, and dominance of sands. Winds are the most widespread geomorphic agents in the desert environments, arid and semi-arid regions. Height of action. Wind erosion generally takes place above the ground, and thus wind velocity plays a major role in determining the degree of Aeolian erosion. Wind erosion is effective only up to 180 centimeters above the ground surface. Maximum wind erosion occurs at short distances. Unlike rivers and glaciers, winds erode the rocks from all sides because of their variable directions. Deflation and transportation develop parallel with accumulation, giving rise to specific relief forms and types of Aeolian continental deposits and landforms. Erosional landforms. The erosional landforms of the wind are blowouts, deflation basins, desert pavements, desert varnish, ventifacts, and mushroom rocks or pedestal rocks. Blowouts. The most effective agents of abrasion are sand grains. Rocks that are exposed to the sand blasting of prevailing winds become pitted, grooved, and polished. Deflation basins, called blowouts, are hollows formed by the removal of particles by wind. Sand grains are rolled or skipped along the surface and comprise the bed load. In such a way, the entire bed is lowered, in some cases up to 1 meter, resulting in shallow depressions called blowouts. This depression may be a few meters to as much as a kilometer across. Blowouts are found on rock surfaces subjected to disintegration by weathering. Deflation basins. Deflation basins are depressions formed in the deserts due to removal of sands to a greater extent. The size of the depressions vary from small valleys to big hollow deeps. Desert pavement. A desert pavement is a typical desert surface. It is covered with closely packed, interlocking, angular or rounded rock fragments of pebble and cobble size, formed by the gradual removal of the sand, dust, and other fine-grained material by the wind and intermittent rain. Stone or desert pavements are larger stones set in or on a matrix of finer material. Desert pavements are only 1 or 2 fragments thick that form a mosaic in a matrix of fine sediment. Coarse fragments are alluvial pebbles, gravel, and cobbles, or debris weathered from the bedrocks. Desert pavements cover areas ranging from a few square meters to hundreds of square kilometers. They occur mostly in sand poor regions. Desert varnish. Desert varnish is a dark coating on rocks found in arid regions, composed dominantly of fine grained clay minerals containing black manganese oxide and red iron oxide. Varnish can be a prominent feature in many landscapes. It often coats canyon walls. Earlier, it was believed varnish was made from substances drawn out of the rocks it coats. Microscopic and megascopic observations show that a major part of varnish is a clay, which could only arrive by wind. Clay acts as a substrate to catch additional substances that chemically react together when the rock reaches high temperatures in the desert sun. Wetting by dew is also important in the process. Desert varnish has a high concentration of manganese, 50 to 60 times more abundant than elsewhere. Black manganese oxide or birnacite and red iron oxide or hematite add color. Desert varnish forms only on physically stable rock surfaces that are no longer subject to frequent precipitation, fracturing, or sand blasting. Desert varnish often obscures the identity of the underlying rock, and different rocks have varying abilities to accept and retain varnish. Limestones, for example, typically do not have varnish because they are too water soluble and therefore do not provide a stable surface for varnish to form. Shiny, dense, and black varnishes form on basalt, fine quartzites, and metamorphosed shales due to these rocks' relatively high resistance to weathering. Ventifacts. Ventifacts are stones faceted or planed by abrasion. With changing direction of dominant winds, different facets merge along sharp ridges to transform rounded stones to angular ventifacts. The facets can be worn into the face of the rock, oriented into the prevailing wind direction. Yardangs. Yardangs are wind abraded ridges oriented with the prevailing winds and separated by abraded chutes that conduct wind-blown sand. Yardangs are larger hill-sized features sculpted by the wind. Yardangs are composed of cohesive silts and clays, sandstone or limestone. They develop in regions with strong unidirectional winds. Many of them are during dry, windy periods of Pleistocene. The meso-yardangs are generally a few meters high and 10 to 15 meters long. They are more common and can be found throughout the Sahara. The micro-yardangs are only a few centimeters high. Mushroom rocks. Mushroom rocks are the exposures having broad upper part and narrow base carved by the action of wind over an existing standing rock mass. A mushroom rock, also called rock pedestal or a pedestal rock, is a naturally occurring rock whose shape, as its name implies, strikingly resembles a mushroom. These are usually found in desert areas. They are formed over thousands of years when wind erosion of an isolated rocky outcrop progresses at a different rate at its bottom to that at its top. Occasionally, the chemical composition of the rocks can be an important factor. If the upper part of the rock is more resistant to erosion and weathering, it will erode more slowly than the base. Pedestal rocks. Pedestal rocks are called as Gara in Sahara. Undercutting is a marked feature of wind abrasion. It is most effective within 30 to 60 centimeters of the surface where saltating sand is abundant. Rocks formed by undercutting are known as pedestal rocks. Oasis. In geography, an oasis, plural oases, is an isolated area of vegetation in a desert, typically surrounding a spring or similar water source. Oases also provide habitat for animals and even humans if the area is big enough. The location of oases has been of critical importance for trade and transportation routes in desert areas. Transportational effects. Wind transports sediment near the surface by saltation. Just as in the bed load of streams, saltation refers to short jumps of grains dislodged from the surface and jumping a short distance. As the grains fall back to the surface, they may dislodge other grains that then get carried by wind until they collide with ground to dislodge other particles. Smaller particles can become suspended in the wind and may travel for longer distances. How does wind transport sediment? Bedload are the sediments that are too large or heavy to be carried away by water in suspension by water or wind. The suspended load is the silt and clay-sized particles that constitute most of this load, held aloft for many miles. The particles that are transported by winds may go through suspension, salutation, skipping or bouncing, and creeping, rolling or sliding along the ground. Small particles may be held in the atmosphere in suspension. Upward currents of air support the weight of suspended particles and hold them indefinitely in the surrounding air. Typical winds near Earth's surface suspend particles less than 0.2 millimeters in diameter and scatter them aloft as dust or haze. Saltation. Saltation is the transport of sand grains in long 1 meter or more, low within 1 to 2 meter of the ground, trajectories as momentum is passed from grain to grain. Most of the transport of dune sand happens through saltation. At high wind speeds, saltation is more or less continuous. Saltation is downwind movement of particles in a series of jumps or skips. Saltation normally lifts sand-sized particles no more than 1 centimeter above the ground and proceeds at 1/2 to 1/3 the speed of the wind. A saltating grain may hit other grains that jump up to continue the saltation. A grain may also hit larger grains that are too heavy to hop but that slowly creep forward as they are pushed by saltating grains. Surface creep. Surface creep accounts for as much as 25% of grain movement in a desert. Creep or traction is a movement of coarse sand and pebbles up to 6x larger than saltating grains as they slide and roll, impacting one another and transferring momentum. It usually does not occur with velocities less than 4.5 meters per second. Air over deserts is cooled significantly when rain passes through it. This cooler and denser air sinks towards the desert surface. When it reaches the ground, the air is deflected forward and sweeps up surface debris in its turbulence as a dust storm. Wind velocities. At wind velocities of up to 6.5 meters per second, dust and fine sands of 0.25 mm diameter are carried. At 10 meters per second, the wind can lift and transport particles of 1 millimeter in diameter. At 20 meters per second, particles of 4 to 5 millimeters diameter are transported. Hurricanes can carry even small stones. The dust of African deserts is transported by strong trade winds over distances of 2,000 kilometers to 2,500 kilometers. Sometimes the dust and particles may obscure the sunlight. Depositional landforms. Sandy Aeolian deposits are distinguished from other continental deposits by a number of specific features. They are irregular cross bedding, gentle dipping, steep and orienting in different directions. Aeolian deposits are relatively small in size. The particles may range from 0.05 to 0.25 millimeters in diameter. Dust particles are almost completely absent at the location of deposition. The grains of Aeolian sands are generally well rounded due to prolonged transportation by wind. Sometimes they are well polished. The depositional landforms of wind are ripples, sand dunes, erg, sand sheets, sand shadows, loess, and takairs. Sand ripples. Sand ripples occur as a result of larger grains accumulating as smaller grains are transported away. Ripples form in lines perpendicular to wind direction. Wind-blown dust. Wind-blown dust are sand-sized particles, generally do not travel very far in the wind, but smaller-sized fragments can be suspended in the wind for much larger distances. Ripples. Ripples are small sand waves created with a wavelength of about 1 meter, that is, the typical path length of saltating grains. They are ephemeral and mobile, that is, move, disappear, and reform during wind storms. These are common in the windward slopes of sand dunes. Dunes. Dunes are classic Aeolian landforms. They are stable or advancing landform of wind-blown sands. They originate as a mound of free sand from a sandy, surficial deposit or from a blowout. As the mound grows, it develops the dune asymmetry, characterized by a gentle windward slope and a leeward slip face at the angle of repose for sand. Dunes are much less mobile. They migrate downwind as sand saltates up the windward face. Dunes classified. Dunes are further classified into the following types: Barchans dunes, Parabolic dunes, Transverse sand dunes, and Longitudinal dunes. Barchans. Barchan dunes are classic asymmetric crescent-shaped desert dunes. They develop perpendicular to the prevailing wind. These are isolated, freely migrate across desert plains, maintaining their forms. Their characteristic feature is their wings. They have a long and gentle windward slope, 10 to 15 degrees, and short and steep leeward slope. Barchans range in height from 1 to 2 to 15 meters. Occasionally, they raise a height of 20 to 30 meters. Their width may go up to 140 meters. Parabolic dunes. Parabolic dunes are associated with vegetation, so form in subhumid and semi-arid environments, rather than arid zones. They initially originate as blowouts, and the dune forms as the head of the dune at the downward edge of the blowout. Transverse dunes. Transverse dunes are linear, cuspate, ridgy sands formed perpendicular to the wind with large sand supply and low winds. With stronger winds, they may evolve into barchans. They usually occur on beaches, floodplain alluvium, or erodible sandy bedrock rather than the dry deserts. Longitudinal dunes. Longitudinal dunes are linear forms parallel to the strong persistent winds. They are called as seef. They form in dry subtropical deserts with irregular sand supply. They are separated by lag gravel. Whalebacks. Whalebacks are ridges of coarse sand left in the path of a migrating longitudinal dune. Ergs. Ergs are sand seas. They are very vast sand sheets. They cover about 1/4 to 1/3 of the area of true deserts. These sandy deserts overlie the poorly consolidated sandy bedrocks. Sand sheets. Sand sheets are flat, gently undulating sandy plots of sand, surfaced by grains that may be too large for saltation. The surface is usually rippled. Pits generally display layers of two distinct grain sizes. This is due to the fact that larger grains are transported by creep while smaller ones saltate. Sand sheets are formed on borders of deserts having scanty vegetation. The fixed sand sheets are undulating sandy hills in subhumid environments. The Selema sand sheet, which occupies 60,000 square kilometers in southern Egypt and northern Sudan, is one of the Earth's largest sand sheets. Sand shadows. Sand shadows are accumulation of sand on either side of a fixed obstacle. Example, shrub or tuft of grass. Sand drifts. Sand drifts are accumulation of sand in the lee of a gap between obstacles or in the still air at the base of an escarpment. Loess. Most of the dust carried by dust storms is in the form of silt-sized particles. Deposits of this wind-blown salt are known as loess. Loess is a homogeneous, typically non-stratified, porous, friable, slightly coherent, often calcareous, fine-grained, silty, pale yellow or buff, wind-blown Aeolian sediment. It generally occurs as a widespread blanket deposit that covers areas of hundreds of square kilometers and tens of meters thick. Loess deposits are unusually fertile. They are also used for building construction. The thickest known deposit of Loess, 335 meters, is on the Loess Plateau in China. Loess tends to develop into highly rich soils. Loess deposits are geologically unstable by nature and will erode very readily. Tuckairs. Tuckairs are flat, smooth, clayey deserts ranging in size from a few square meters to several square kilometers. They develop as separate basins. A tuckair is usually formed in a shallow, depressed area with a heavy clay soil which is submerged by water after seasonal rains. After the water evaporates, a dry crust with fissures forms on the surface. Conclusion. Wind is a major geological agent. It changes the landscapes of arid and semi-arid regions with new landforms. It is a highly dynamic system forming unstable landforms. Wind-created landforms are subjected to wind action again and again. Understanding of their movements and deposition is a basic requirement in earth and atmospheric sciences.